Okay, our next example is also familiar. We learned that in the first chapter, chapter 23. Remember, we had studied the electric field produced by a uniform ring on its axis of symmetry if the ring is uniformly charged. Okay, we can revisit this problem, this time by calculating the electric potential at point P, somewhere on the axis, and then from that potential we're going to calculate the electrostatic field at point P. See if we get the same result as we got before. Now, what's the advantage of calculating electrostatic potential instead of the electric field? Well, it's because it's a scalar quantity, right? We don't have to worry about x direction, y direction, components, that sort of thing. So, what is the electrostatic potential produced by this uniform ring? Well, it is an extended continuous object, and therefore we have to break it into infinitesimally small pieces. So here's one little piece here. The charge is dq. Okay, what is the electrostatic field produced by? The electrostatic potential produced by this little piece dq at point P? All you have to do is to draw a line connecting them. The length is r. This is 90 degrees. Okay, the radius is a, and the distance between the center of the ring and the point of interest on the x-axis is x. Okay, let us find dV produced by dq. So dV, that's just the point charge, so it's k dq over r, okay, over r. And then we can integrate. Don't worry about the x direction, y direction. It's just a scalar, so let's integrate. So v at point P, okay, equals the sum of that. Now, does r change as you go around the ring? R doesn't, right? So take these out, take the r out, so it's k over r. You're left with the integral over dq, and that just total charge q. So it's k q over r. Big Q is the total charge carried by this uniform ring. So this is the electrostatic field at point P. Now, once you get that, how does one calculate the electrostatic field, E? Okay, as we learned that in the x direction, E of x, what is that equal to? Negative dVp dx, right? That's how we calculate that. Now, be careful here. This expression does not have x explicitly. So let me first rewrite this expression so that x shows up instead of r. And then we can easily do that. So this is just negative k. I'm taking that constant k out. D dx of what? kq. I'm going to take k, both k and q out. 1 over r is really just 1 over the square root of what? A squared plus x squared, right? A squared plus x squared. So to get the electric field, all I need to do is to finish this differential, which is not that hard to do. It's a squared plus x to the power negative 1/2. Okay, to the power negative 1/2. So work it out. It's negative 1/2. Negative cancel with that negative. K q over 2, right? And then a squared plus x squared to the power negative 3/2. So it's a squared plus x squared to the negative 3/2. And then don't forget there is also a 2x when you finish the differentiation. And 2 and 2 cancels. You're left with this result: k q x divided by a squared plus x squared to the power 3/2. If you go back to chapter 23, take a look at our notes, you find that was exactly the right expression that we obtained for the electrostatic field at point P on the axis of a uniformly charged ring. So you see, again, an alternative way of obtaining the electric field. We didn't really do any vector calculation. We didn't have to, figure out that the fact that the electric field points that way. It just comes out naturally. Okay, our next example is a little bit more involved. The setup is now a uniformly charged sphere. It could also be a uniform spherical shell. In other words, it's empty inside, all the charge is on the surface. Okay, suppose suppose the total charge Q is positive, so the potential is higher around here, and as you move away from here, move away from positive charge, the potential goes down, right? And let's set the 0 point of the potential at infinite far away for simplicity. Okay, what I want to know is what is the potential V as a function of R, You know it's 0 at infinity. How should it increase? And in particular, what is value at the center of the shell, of this sphere? How does one do that? Well, be careful, because the field expression is different inside and outside the sphere. Okay, so when we calculate, the integral of E dot dr, we have to separate it into two segments, inside and outside. In general, once again, let me recall that formula. V initial minus V final equals initial to final E dot ds. That is always the general formula. And what I want to do is I want to take a particular path to calculate V. And since the field is radial, right? It's radial, so might as well choose this axis. Okay, so I'm going to pick up a path simply one-dimensional on this axis, so I don't have to worry about any three-dimensional consideration. And suppose you start from a certain point R, a distance R away, certain point P, a distance R away from the origin. Okay, and you move out radially. You can move in and move out. Let's say we move out all the way to infinity. Right? So in other words, initial point is point P, final point is infinity. Okay, then how should we rewrite this formula? If I start from initial point at point P and going further out radially, then I would write Vp minus V at infinity equals initial location, this distance is R, okay? Final location is infinity, right? Now, the nice thing about choosing this direction is that as I move out, ds, this ds here is just dr, right? It's just the vector dr. And furthermore, E and dr, or E and ds, they have the exact same direction, they're both radially outwards because of the symmetry of the problem. So this I can write as just EDR. Okay, just as EDR. E is not a constant though, I cannot take it out. Now, V infinity, I'm going to set it to 0. So therefore, Vp is just the integral of R to infinity EDR. It's just that simple. Now, at this point, let's be careful. If we're looking at a point P outside the sphere, then it doesn't matter whether the sphere is stuffed uniformly with a charge or it's just an empty uniform shell. Why? Because in both cases, the electrostatic field outside the sphere is the same as if all the charges are concentrated at the center. So E would have the same exact expression from that point P outside the sphere all the way to infinity. In other words, you cannot tell the difference just by looking at the electrostatic potential outside. You cannot tell whether it's a solid or an empty shell. Okay, so for V, so let's consider the case if R, this R is greater than the radius of the sphere, then it doesn't matter whether it's a uniform sphere or spherical shell. I find that E is always equal to KQ R squared, right? And then we can readily insert this into here and can finish this integral. Then I get Vp equals to what? R to infinity KQ over R squared dr. And we can easily finish this integral, and that turns out to be just KQ over R. It's just that simple. Okay, it's just that simple. That is when you have a point outside the sphere. You always get that, whether the sphere is empty, whether it's hollow or solid. Now, the situation becomes more interesting when you look at a point inside. Okay, we look at a point inside. Look at a point inside, then it makes a difference whether it's a solid sphere or whether it's a shell. First of all, if it's a shell, uniform shell, what is the electrostatic field inside the shell? Well, that's just like Newton's theorem, shell theorem, right? We learned that from the previous chapter, Gauss's law. You know what the result is? The field is what? 0 inside, right? Now, when the field is 0, okay, here's a very important question. If the electrostatic field E is equal to 0, what is the corresponding potential, electrostatic potential? Is it also 0? Okay, in other words, when E is equal to 0, does that mean V is also equal to 0? How is E and V related? Now be careful here. This is how E and V related. Okay, when you plug in E equal to 0, and when E is equal to 0, that integral is what? Is 0. Does that mean V equal to 0 though? No, it only means V initial equals V final, right? That means when you go from initial to final position, you start from initial and go up to a final. If there is no electric field you encounter from here to there, then what you can say, all you can say is that the electrostatic potential does not change. Okay, V initial equals V final. Does that mean the electrostatic potential equals 0 though? No, it doesn't. It only means the electrostatic potential is a constant, which does not change from location to location. Okay, so what is the value of the electrostatic potential inside when if it's a uniform spherical shell? Well, all we know is that since there is no electric field inside, the electrostatic potential is a constant. Okay, it's uniform throughout. It's not necessarily 0. So what kind of constant is it? Well, if I were to draw a diagram, okay, if I were to plot the electrostatic potential as a function of R for an empty shell. Okay, this is the empty shell, not a solid sphere. This is the radius, right? Further away from the radius, in other words, outside the shell, you know the electrostatic potential behaves like that. Yeah, that expression, right? At that particular location, what is the value of the electrostatic potential? It is equal to KQ over big R, right? KQ over big R. So you can use that formula all the way up until the surface of the conductor of the shell, but you cannot go in. When you go in, this formula ceases to be valid because all of a sudden the electrostatic field drops to 0. Okay, drops to 0. But what happens to the electrostatic potential? Is it 0 inside? If it were 0 inside, then you will see a discontinuity between the field, the V value inside and V value outside. We know that the electric field itself is discontinuous across this shell. But what about V? Can V be discontinuous? All right. Let's see what it takes for V to be discontinuous. See, if V is discontinuous, look at this formula here. You start from initial point, which is right outside the shell, right? You go into a point right inside the shell. So what is V initial, what is V final? And suppose they're not equal to each other, which means there is a discontinuity. It drops, it changes suddenly. V changes suddenly from here to there. Okay? But that is equal to this integral. And this integral is over an extremely short range, right? Right outside to right inside. So R initial and R final are almost equal to each other. So the range of this integral is extremely small, and yet you produce a non-zero result. What does that tell you about E, the E field? When you take R initial and final to be almost equal to each other, both almost equal to the radius, right? Normally, when you multiply a very short distance by the electric field, you're not going to get any non-zero value unless E is what? Very, very, very large. Okay? So, the only reason why the potential will have a discontinuity is because you encounter a region of infinite electric field. Is that happening here? Well, is the electric field anywhere infinity for an empty shell? No, it's equal to something like KQ over R squared outside, and it's 0 inside. It's never infinity. Okay, so what can we say about the continuity of the electric potential? Well, it has to be continuous, right? Unless E is infinity at that point. If it's not infinity, then VI and V final should be equal if I is right here and if F is right there. So that means the electrostatic potential right inside the shell should be KQ over big R, right? Otherwise you will have to jump. And once it is this value here, as you move around inside the shell, would it ever change? No, because the electrostatic field E is 0. So the potential, once it's a certain value inside, it will be the same value throughout the entire empty shell interior. So therefore, I conclude that the electrostatic field potential should be just a flat line like this, okay? Just a flat line, and then it goes like an over R outside. This is how you calculate the electrostatic potential distribution of a uniform spherical shell. Okay, so it goes up like this until KQ over R, and then it stays the same constant all the way to the center. So what's the electrostatic potential at the center? It's just KQ over big R. That is the case for uniformly charged spherical shell. Okay, naturally what we consider next is a uniform solid shell. I mean solid sphere, not a solid shell. What is the electrostatic potential at a point P inside that sphere? Okay, the formula we use following the previous page is Vp equals R to infinity E dr. R is, a distance between here and there. From point P, we integrate all the way to infinity. And again, since the electric field inside and outside are not the same, we're going to break this down into two pieces. Okay, break the integral down to pieces. R to the radius of the sphere, which is big R, E dr, and then from big R all the way to infinity, E dr. Now we know how to calculate the second integral, okay? Because once you're outside the shell, outside the sphere, the electric field is just KQ over R squared. So that part is simple. That part I know what it is. It's just KQ over R, right? Because it's just KQ over R squared, you integrate, that's what you get. Now, this integral, I must first obtain value of E, the electric field E. What is the electric field E of a uniformly charged sphere inside of it? We learned that, again, from the previous chapter. We learned that. You recall, did you recall, that it is a linear function, right? It starts from 0 in the middle and grows linearly outwards. So it's K Q R over big R to the power 3. Remember that? And then dr. Okay, now we can easily finish the second integral, and this is what we get. We get KQ over R plus everything's a constant except this R here, so it's 1/2. Okay, so it's KQ over R squared, 1/2 of R squared, and you integrate between the upper limit is, the lower limit is small r, the upper limit is big R, and we can easily simplify that. So that's what you get after you combine these two terms. It's KQ over 2R and then times this factor here. This small r value has to be less than big R because it has to be inside the solid sphere. Now take a good look at this expression here. Okay, this expression, when big R and small r are equal, so you're right on the surface of the solid sphere, what does it give you? Well, it just gives you 3 minus 1 here, which is 2, and 2 over 2 cancels, just KQ over R. So again, the expression for the electric potential outside the sphere would still be KQ over R up to the surface. So this is just same thing here as before. Okay, KQ over R. There is no discontinuity. The electric field, electric potential right inside and right outside the sphere is the same whether the sphere, if the sphere is solid. Now, what is interesting though is what happens when you get even further in. When you get even further in, okay, here's the origin, Suppose you make R smaller, in other words, you get further and further in. You're getting closer and closer to the center. What happens to the potential? It should rise, right? Should rise. And indeed, that is true. It rises. It goes from KQ over big R at the surface, all the way to what? 3 over 2 KQ over R. Okay? And the shape of this is the only variable part. The shape looks like it's an inverse parabola. Okay, so it's a parabola R squared, but it was a negative sign. So it's an inverse parabola. So it looks like that. All right. And what's the highest point here? What's the highest point here? You see, this point is KQ over R. The highest point in the middle is 3 over 2 KQ over R. That is the electrostatic potential in the middle. And you can also show that this inverse parabola and this 1 over R curve cross over neatly so that the derivative is actually continuous between here and there. And that is important because the derivative of V with respect to R gives the electric field. Okay, so the electric field is continuous going from here to there, unlike the case of a shell in which the electric field actually abruptly changes because you go across two-dimensional charge distribution.